Hi, my name is Robert McMillan, and today I'm going to talk about the mathematics behind emulsion polymerization. This is in relation to a project that I've been working on for the last 6 or 7 months on creating a scalable and continuous emulsion polymerization platform to aid in the research and development of latex formulations, which are the main output of emulsion polymerization. I'm going to begin by talking a little bit about emulsion polymerization with some background information. I'll then introduce the kinetic models, and then I will show you guys how they were solved, and then finally some experimental results with a traditional emulsion polymerization system, which is typically in a batch reactor, and then my continuous platform, and see how they line up. So first, a little bit about emulsion polymerization. It's a radical polymerization process where the monomer is dispersed into an aqueous phase that contains surfactants and initiators, or initiator molecules. So a surfactant is a molecule that has a hydrophilic head and a hydrophobic tail. You can think of this as sort of like the phospholipids in your cellular membrane, or the lipids in your cellular membrane. And in traditional emulsion polymerization, the surfactant concentration is high enough to form what are called micelles. So that's a purely thermodynamic phenomena where, again, if the concentration of surfactant molecules is high enough, they'll tend to aggregate together in these micellular structures where the hydrophilic head is pointed outwards towards the continuous aqueous phase, and the hydrophobic tail is pointed inwards to create a hydrophobic environment on the internal micellular structure. Now, because the internal micellular structure is hydrophobic, monomer will tend to diffuse and collect inside of those micelles. So those are called monomer swollen micelles. Now, during that diffusion process and during emulsion polymerization, the monomer molecule could come into contact with an initiator radical, which I've shown here. This is a persulfate ion decomposing into radicals. And here it is radicalizing a styrene molecule, which is some of the experimental data that I have to show. So once the radical is formed, it could enter into either a monomer swollen micelle or an existing polymer particle where a radical has already made entry. And once the radical is inside the monomer swollen micelle, polymerization begins. And so the way I like to think about the overall emulsion polymerization process is there's a bunch of these little polymer reaction centers that are forming polymer particles throughout the aqueous mixture. So there are 7 different reactions that need to be accounted for in a population balance on the number of particles formed, and thus the overall polymer that's formed. So the first reaction, this is row A in the table at the top of the slide, is the initiator decomposition into 2 initiator radicals. So once the radical enters a non-nucleated particle, it turns into what's called an active particle, represented by N star, which is the total number of active particles. And this happens when a radical enters a micelle, so it's 1 radical plus 1 micelle goes to an active polymer particle. If the polymer particle, or if the radical enters an active polymer particle, termination occurs in which the active polymer particle is no longer active, but it's still a polymer particle, and that's represented by this letter N here, which is the total number of polymer particles. Also called a dead polymer particle. The dead polymer particle can be reinitiated by a radical and thus can go back to being an active polymer particle. And so you can see here that the active polymer particles and the number of dead polymer particles are both functions of time. The rows E and F describe the propagation or the reactions that occur inside of a polymer particle. So row E represents the propagation in a particle where a monomer enters, it's not a radical, and there's a growing polymer chain inside that polymer particle. And so the monomer adds onto that chain, and we have now a polymer chain of length J+1, and it still has that radical on it. Another thing that could happen is, in contrast to row E, again, a non-radical monomer molecule enters, and there's a reacting polymer chain in there. And instead of adding the monomer onto the polymer chain, it just transfers the radical to the monomer. And so we result with a polymer chain with no radical, and instead a monomer with a radical. The last one is what's called chain transfer agent reaction. And what happens is a polymer chain with a radical transfers the radical to a chain transfer agent T. So the chain transfer gains the radical, and the polymer particle, the polymer chain doesn't increase by any length. Very similar to row F, but instead of a monomer, it's a chain transfer agent. Now, I didn't have to deal with this because I didn't include any chain transfer agents, which also simplifies it. So if we write up some expressions for all of these reactions, we end up with a system of 4 differential equations to express the change in conversion over time, which is also the total rate of polymerization. So as I mentioned before, once a radical enters, we form these active polymer particles, which is represented by this top equation here. And it's dependent upon, and its expression is the rate of initiator decomposition times 1 minus 2 times the already existing number of active particles divided by the total number of particles, which is the total dead number of particles, those with no active radicals inside, plus the number of active particles as shown here in the second expression, plus the surfactant concentration present in micelles, this equation here, divided by epsilon. Now, epsilon is an extremely important factor in this system of equations, and it is the only adjustable parameter. Though it is a thermodynamic quantity, which means that if I have the same concentration and I have the same temperature, then I should have the same value of epsilon, whether the reaction is occurring in a flow scenario or a batch scenario. So as you can see, this is a nonlinear set of ordinary differential equations, so they have to be solved simultaneously, and there is no analytical solution present, which means we're going to have to solve them numerically instead of by hand. So to do that, I utilize Python, and specifically the Runge-Kutta methods in Python using SciPy's integrate ODE pack. And the Runge-Kutta method works by constructing these 4 lines for the 4th order Runge-Kutta, and then adding their predicted values of y together with a weighting fraction. Now, the interesting thing about the Python implementation of this is that it actually uses the 4th order Runge-Kutta method to approximate the new y value, but it uses the 5th order Runge-Kutta method to get the optimum step size h. So what happens is, for each time point that we're integrating over, we calculate the 5th order Runge-Kutta approximation, and then using that, we get the optimum step size of h, and we plug that back into the 4th order approximation to get our new y value at each point. So we do this for each point along our discretized time, and we do that to solve the system of differential equations. So we'll do that 4 times for each of the 4 equations shown on the last slide. So next, I also had to deal with fitting the epsilon value to my experimental data. To do this, I also utilized Python, and specifically Brent's method for minimization. So Brent's method for minimization combines the secant method for minimization, which we've all seen, as well as the bisection method for minimization, which you've also seen. The reason why this is done is because the secant method can tend to diverge to infinity, and so you might not find a solution there, but it's computationally very quick. So what happens is you iteratively calculate a new value for your minimum based upon your last values minimum of your last value calculated, beginning with some guess. So what happens is for each iteration, a value is calculated using the secant method and a value is calculated using the bisection method. And if the function value at xi and the previous value, so this is our current iteration, and our previous value of iteration are extremely close, you can see this quantity is going to go very quickly to infinity. So in this case, the Brent's method will choose to use the bisection new guess, which again is computationally slower, but extremely robust and doesn't suffer those issues. It'll use that as its new guess rather than, or its new value rather than the secant method. So this basically combines a computationally efficient method that has error associated with it to a computationally inefficient method with very little error to converge much faster to an accurate solution. So I utilized this and that system of differential equations to fit to kinetic data that I obtained in the lab. So the first plot on the left here is the batch data, which I used to find the correct value of epsilon. And as you can see here, the kinetic value, the kinetic model and the observed conversion lines up pretty well. I then took that same set of differential equations with my now fitted epsilon value, which again is a thermodynamic variable, which means that if in a continuous reactor scheme, which is again what I used in my platform, I should have the same value of epsilon in both these systems because my concentration is not changing and I'm at the same reaction temperature. And what we find is that the conversion values for two residence times at two different Reynolds numbers in the plug flow reactor far overshoot what the model predicts. What we are anticipating is occurring is that we are artificially decreasing this value of epsilon in favor of forming new particles, and we're getting a much higher number of particles at a smaller size. So hopefully we can use this information to get much faster conversion for a given time that we might have to wait to run experiments, and thus facilitate the quick screening of new adhesive formulations, as well as possibly control the particle size. So at a smaller Reynolds number, I'm not forming as many particles, which means I'm going to have a higher size. And at the higher Reynolds number, I'm getting, again, that artificial decrease in epsilon, which means I'm forming much more particles, but they're not able to grow as much because that conversion is taken out by the formation of new particles rather than the growth of existing particles. So hopefully we can use this to tune the size of particles that are formed, which is an important property in a lot of latex formulations, as well as having faster conversion for a given time point. So I hope you saw how we can numerically solve systems of ordinary differential equations in Python, as well as find the minimized error between observed points and model points to get a fitted parameter.